In this video, we will talk about how to estimate marginal cost with partial derivatives. So I want to begin with an example right away, which says a store's daily cost to manufacture X pints of ice cream and Y pints of frozen yogurt is given by this function C of X comma Y, and the units are hundreds of dollars. When 10 ice cream pints and 6 frozen yogurt pints have already been made, part A asks, find the exact cost of the 11th ice cream pint. All right, so when this question tells us that, or it asks for the exact cost of just the 11th ice cream pint, it means that 10 have already been made. Already been made. So to get the exact cost of the 11th ice cream pint, we need to know how much would 11 ice cream pints, given that we have already made 6 frozen yogurt pints, cost, and how much would 10 ice cream pints with 6 frozen yogurt pints cost, and just subtract the difference. Okay, so I need to plug in 11 for ice cream, and frozen yogurt's got to stay at 6 because that's the level that we're at. And then we got to plug in 10 for ice cream, and ice cream is X, which is why I'm plugging it in for the X and keeping Y as 6. So when we do that, if I plug in 11 for X and 6 for Y, we get 4 times 11 squared plus Y squared, so that's 6 squared, let's try that squared a little bit better, squared plus 5 square rooted all over X plus 2, so all over 11 plus 2. And then minus, now I plug in 10 for X, 6 for Y. That gives me 4 times 10 squared plus 6 squared plus 5 in a square root all over X plus 2 is going to be 10 plus 2. And this we could simplify. So this first fraction ends up being square root of, if we work it out, 525 over 13 on the denominator minus this next term ends up simplifying really nicely. This square root ends up just simplifying to 21, and then we have 12 on the denominator. And with this, I'm going to plug it into a calculator, and it ends up being approximately 0.0125, rounding it to 4 decimal places here. And what are the units? Well, the units of cost are hundreds of dollars. So $100. Okay. So it's a little bit weird to write some sort of decimal, small decimal like this in $100. So I could convert this to just dollars if I multiplied this decimal by 100. And that's going to move the decimal over 2 spots to the right. So this is $1.25. Okay, so not a very high cost for that 11th ice cream pint. Okay, so what if now, in part B, I want to estimate the marginal cost of ice cream pints at this level? Because in part A, we found what's called the exact marginal cost. How much more does one extra, in this case, ice cream pint cost? Part B is asking us to estimate it. So we are going to get a function that lets us estimate the marginal cost. And it's going to end up being a little bit more efficient because we'll end up just plugging one value into it to end up getting an estimate, rather than what we did above, which was plug in 2 different points and subtract. That's why sometimes it's more helpful to get an estimate. It's just more computationally efficient. Okay, so how can we estimate the marginal cost? So what I need The marginal cost is the cost of one extra ice cream pint in this case. So I need to know how much does my cost change. I'm going to denote that as delta C. Delta is just a notation for change in. So this is change in cost. I need the change in cost when the number of ice creams goes up by 1. So that means the change in X is going to be 1, while my Y value is constant. The Y value remains fixed. It is, in our example, it's 6. So what we'll use is the partial derivative. I'm going to try to get del C, del X. So a partial derivative is an instantaneous rate of change, which I'll denote as IROC. And we can approximate an instantaneous rate of change with an average rate of change. So del C, del X is going to be approximately equal to the change in C over the change in X. So more generally, let's pick a different color here. This is, on top, it's a change in the output of my function, the cost, over a change in the input, because we're letting the X change a little bit. It's increasing by 1. So that is the general form of an average rate of change. It's a change of output on top divided by a change of input in the bottom. Average rate of change. So we are going to estimate this partial derivative using the average rate of change. In other words, we're going to use the fact that this instantaneous rate of change is approximately equal to that average rate of change. So the left-hand side is just that partial derivative. And on the right-hand side, we get delta C on top. But delta X we know is 1. So delta C over 1 is delta C. So now we need to get this partial derivative of C with respect to X. So remember what our cost function was. Okay, so I've copied it in here in this little corner. And I want to give you the opportunity to try this. Okay, so pause the video for about 2 minutes and see if you can compute this partial derivative with respect to X. 4, 3, 2, 1, pause the video. Pause the video and try to compute this partial derivative for about 2 minutes. Alright, so hopefully you've done that. Hopefully you've paused the video for about 2 minutes to try this. Okay, so first, to do this partial derivative, I'm going to make one simplification, which is to rewrite that square root. So let's see, we can rewrite this square root. Ooh, if I can get that to erase better. Alright, so there we go. So the square root I can rewrite as that whole thing to the 1/2 power. And so because I see an X on the top and this X on the bottom, it looks like we're going to have to use quotient rule. And whoops, looks like I erased that plus sign accidentally. So let's put that back in. Okay, so with quotient rule, we are going to get the function on the bottom. Sometimes I call that low. And then d high, so derivative of the top. So that's going to involve chain rule. I'll get the 1/2 coming down, and then the function inside stays the same. 4x squared plus y squared plus 5. Subtract 1 from the power, so we get negative 1/2. And then multiply by the derivative of the inside. In this case, we're taking the partial of this with respect to x, which is going to give us 8x for the first term. And then y squared gets treated as a constant, so that's going to be 0 for its derivative. And the derivative of 5 is going to be 0, because that's a constant. Okay, so low d high, bottom function times the derivative of the top, minus high d low. So high means the function on the top, 4x squared plus y squared plus 5 to the 1/2. And then d low means the derivative of the bottom with respect to x here will just give us 1. Because that's the derivative of the x, and the derivative of the 2 is 0 because it's a constant. Okay, so all over low squared, all over the bottom squared, which is going to give us x plus 2 quantity squared. All right, so that's our partial derivative, and it asks us to do this at this level. So this level was described at the beginning of the question. The level we're at is 10 ice cream pints and 6 frozen yogurt pints having been made already. So we're going to plug in those values into this partial derivative. So a notation that I use for that is I write dc dx, my partial. I write a vertical line to indicate I'm going to plug in, and my x coordinate is 10, the y coordinate is 6. So notice I'm not plugging in 11 for x because I have to take my current production level into account, which is I'm at 10 right now, and I'm trying to get up to 11. So that's why I'm plugging in 10. Okay, so if we did this with a calculator, if we plugged into this, I'm going to round. We end up getting 0.0129. And the units here are going to be, the units of cost are $100. And then because it's the marginal cost, it's per item. Because the marginal cost measures the cost of one more item. Alright, so there is our answer. It can also be useful to write that in just dollars. So if I multiply this by 100 to convert it to dollars, this would be $1.29. And it's for the next item. And notice that this is pretty close to the value that we got above, the exact value that we had. And that's good. Okay, so one other comment that I wanted to say about this partial derivative and what it represents is this partial derivative tells us, because it's with respect to x, when x increases by 1, which was what was happening here. So in our problem, it was from 10 to 11. This is going to tell us how much the output function changes by approximately. So the output function is c, and that changes by about 0.0129. So I'm going to put that in a little bubble. So I want to end this video with an important note, which is when a question asks for marginal cost. So if it just says the words marginal cost, and it's a multivariable function like in the example we just did, it's implied that it wants you to estimate it using partial derivatives. If a question wanted the exact marginal cost, like in part A of this example, it would specify that. It would say, give me the exact cost of whatever item we're talking about. So this is really important to keep in mind as you are doing problems on assignments. So in terms of our goals for this section, we finished our third and final goal, which is talking about how we can use partial derivatives to approximate marginal cost in multivariable functions. So this generalized what we saw with one variable functions back in Math 30 in the previous calculus course, where if we had a one variable function, we could find the marginal cost just using the regular derivative.